When there are two functional groups of unequal reactivity within a molecule, the more reactive group can be made to react alone. But it may not be possible to react the less reactive functional group selectively. A group the use of which make possible to react a less reactive functional group selectively in presence of more reactive group is known as protecting group. A protecting group blocks the reactivity of a functional group by converting it into a different group which is insert to the condition of same reactions that is to be carried out as part of synthetic route. For example, the tertiary alcohol here structure 3 could be prepared from a ketoester or acetoacetic ester that is structure 1. If we make phenyl magnesium bromide, that is a Grignard reagent, to react with the less reactive ester group rather than with the more reactive keto group, as expected, simply adding phenyl magnesium bromide to the acetoacetic ester addition to more electrophilic ketone mainly take place. One way of preparing the desired alcohol 3 is to protect the ketone as a ketal. As for example, a ketal protecting group, that is dioxylene, is used in this case. The first step puts the protecting group on to the more electrophilic ketone carbonyl, making it into longer reactive towards nucleophilic addition. The Grignard reagent then adds to the ester, and finally the protection step, removal of the protecting group, that is acid catalyzed hydrolysis of ketal 2, gives us back the ketone carbonyl group. A ketal is an ideal choice here because ketal are stable to base, the condition of the reaction we want to do, but readily cleaved in acid. When choosing a suitable protecting group, the following features must be considered. Protecting group must be simple to put on in high yield. It should be stable to reaction condition and easy to remove in high yield. The ketal protecting group given in the above example satisfy all the criteria, and protecting groups have been designed for most functional groups including alcohol, amines, carboxylic acid and alkenes. They are widely used in a synthesis of complex molecules such as peptide, amino acid, beta-lactam, antibiotics and carbohydrate. Principle of protection of alcohol. The lone pair of electrons on the hydroxyl oxygen of alcohol impart nucleophilicity to them. Therefore, alcohol react readily with oxidizing agents to give carbonyl compounds, and with other electrophile like alkyl halide or acyl halide, they give ethers and ester respectively. Consequently, when electrophilic reagents are to be used in a synthetic step, the reaction at selected hydroxyl sites are to be avoided. The nucleophilic behavior of alcohol must be deactivated. This can be done in two ways. Number one, by putting a bulky protecting group on the hydroxyl oxygen, which can sterically prevent it from competing effectively for electrophiles. For example, here you can see the triphenyl methyl, that is TR ether protecting group where rotation about the OCPH3 bond is rapid and the phenyl ring sweep out a large volume around the oxygen atom to prevent the approach of anything except the smallest nucleophile like proton. By delocalizing the lone pair of electron by conjugation, as for example with a carbonyl system, uh, pivalate ester can be introduced selectively onto 1-degree hydroxyl group and have the additional advantage that the carbonyl is sterically hindered by the tertiary butyl group towards attack by nucleophilic agent. Hydroxyl groups process a readily removable proton with interferes with the action of strongly basic reagent including Grignard reagent and other organometallics that are destroyed by protonation. Replacement of the hydroxyl proton with a relatively inert group avoid this problem. For example, alkyl ethers are especially prepared by Williams ether synthesis or modifications and they survive a wide variety of reaction conditions. However, we cannot use just a simple normal alkyl ether, say for example methyl ether, to protect a hydroxyl group because there is a problem to remove such an ether group. Thus, we need an ether which has features that makes it susceptible to attack by some specific reagent or under specific condition. There are many such groups like THP tetrahydrofuran, MEM benzyl, tertiary butyl, and tertiary alkyl silyl ether. This kind of protecting group can be used for alcohol protection. We will going to discuss in the next slide. Alcohols may be converted into a range of derivatives to prevent their further reaction in synthesis. The choice of protection group depends on the other functionality present within the molecule and the nature of the synthetic transformation to be performed. Ethers, acetals, and ketals cleaved by mid-acidic hydrolysis and ester cleaved by basic hydrolysis can be prepared to protect isolated hydroxyl group. 1,2,1,3 diols can be protected as cyclic ether like acetonides cleaved by acidic hydrolysis and as cyclic ethers carbonates cleaved by basic hydrolysis and some important protecting groups for alcohol we're going to discuss in next slide. Acetals or ketones not only serve as useful protecting groups for aldehydes and ketones, but they also find widespread use in the protection of alcohols. Commonly used ketals include tetrahydropyranyl THP derivatives prepared from dihydropyran in presence of an acid catalyst, the methoxy-ethoxymethyl derivative prepared by reaction of alcohol with methoxy-ethoxymethyl chloride under basic condition and methoxymethyl MOM derivative prepared by the action of alcohol with the methoxymethyl chloride under the basic condition. Acetals or ketols are simply removed by the treatment with aqueous acid. Alcohols may be simply converted to ethers by nucleophilic attack on a suitable alkyl halide. Ethers are stable to basic and mild acidic conditions. They do not react with oxidizing or reducing agents and are inert to organometallic reagents. However, this stability means that many ethers are not easily cleaved to their parent alcohol under mild conditions. Therefore, only certain ethers which are easily cleaved under mild conditions are commonly used as protecting group for alcohol. For example of such alcohol are benzyl ethers, which are converted to alcohol under neutral conditions by catalytic hydrolysis, and tertiary butyl ether, which are readily hydrolyzed with dilute acid, that you can see in this scheme too. Triphenyl methyl uh, trityl group, that is symbolized as Tr, is the most important for the protection of primary alcoholic group. Historically, it was developed for carbohydrate chemistry, but later it was also found very useful in the synthesis of oligonucleotides. Only the primary alcohol react at a useful rate with trityl chloride in pyridine with SN1 mechanism. So selective protection of primary hydroxyl group is possible. This feature is a major reason for using this protecting group. In addition to providing selective protection to primary hydroxyl group, the trityl group offers good resistance to base, but it is easily removed by acid treatment. The milder cleavage conditions are in order TFA greater less than formic acid less than acetic acid. Here the formic acid in ether is sufficiently selective to cleave trityl ethers in presence of either acid selective groups including acetyl, ketyl, benzoic acid and tertiary butyl methyl silyl ether. This is abbreviated as TBDMSOR. The rate of trityl group cleavage can be controlled by substituent on one or more of the phenyl rings. Electron donating group favor cation formation and thus speed up the cleavage process and vice versa. This is particularly useful in the protection of 5-hydroxyl group in nucleotide where more acid labile variants of trityl protecting group can be removed without competing loss of the base. Tricylyl ether derivatives such as trimethylsilyl, that is TMS ethers, have also found widespread use for the protection of alcohol in organic synthesis. These are prepared by reaction of alcohol with trimethylsilyl chloride in the presence of a base. However, trimethylsilyl ethers are not particularly stable and are cleaved under acidic or basic condition and are attached by certain nucleophiles. You can see in this reaction scheme. The mechanism of deprotonation is outlined here also in the second reaction. To overcome the problem of cleavage of trimethylsilyl ether under basic or acidic condition, a number of more bulky trialkyl silyl protecting group have been developed. As already I have mentioned in previous slide, to overcome the problem of easy cleavage of trimethylsilyl ethers under basic or acidic condition, a number of more bulky trialkyl protecting groups have been developed. A certain example is given over here, that is tertiary butyl dimethylsilyl, that is abbreviated as TBDMS, triisopropylsilyl, that is abbreviated as TIPS, and tributyl diphenylsilyl, that is abbreviated as TBDPS ethers, and TBDMS ethers are more stable to hydrolysis than TMS ethers by a factor of 10 raised to 4. Silyl ethers may be cleaved to their parent alcohol by fluoride ion. A convenient source for fluoride ion for this purpose is tetra N-butyl ammonium fluoride, that is BU4NF or TBAF. The use of hydrofluoric acid is not favored due to its corrosive nature. Esters in general prepared from an alcohol and an acid chloride or acid anhydride and carbonate in general prepared from alcohol and chloroformate are cleaved by basic hydrolysis and supplement ethers cleaved by acidic hydrolysis as protecting groups for alcohols. Steric hindrance play a significant role in determining the selectivity of alcohol towards acylation. In general, a 1-degree alcohol can be acylated more readily than 2-degree alcohol. That means primary alcohol can be acylated more easily than secondary alcohol. Among secondary alcohols, those in less hindered positions are more reactive. Tertiary alcohols are acylated only slowly and very reactive acylating agents are usually needed, and the bulky acylating agents exaggerate these trends. These general trends apply also to the acylation of other functional groups. Esters that are most useful for protecting alcohols are described here. The formate ester will going to react with alcohol. 85% formic acid will going to give you formate ester. Alcohol with anhydride in presence of pyridine at minus 20 degree centigrade temperature gives this ester. A formate ester can be cleaved selectively in the presence of an acetate, methyl alcohol reflux or dilute NH3. Formate 100 times faster than acetate or benzoate ester in dilute HNO3. The reaction is given over here. Here also you can see that acetate ester formation is given by different reaction where ether in presence of pyridine as with acid chloride, the alcohol reaction will going to gives us that ester, and its cleavage is given over here in presence of K2CO3 and methanol, or with 50% NH3 methanol will going to get the alcoholic group back. So the protection deprotection is shown over here. Potassium cyanide is a mild trans-esterification catalyst suitable for acid or base sensitive compounds. Here trichloroacetate ester formation is given where alcohol is treated with trichloro acid chloride in presence of pyridine. The cleavage of this, that means deprotection, can be performed by a trichloroacetate ester which is cleaved in presence of an acetate ester in presence of ammonia, ethanol and chloroform, or a formate ester in presence of potassium hydroxide and methanol. So the example of cleavage is also given over here. Here also pivolate ester formation and deprotection cleavage is given. An acetate ester can be selectively cleaved by ammonia in presence of methanol in the presence of pivolate ester. Next is a benzoate ester formation is also given over here. Here alkyl methyl carbonates formation and cleavage, protection deprotection for alcohol is given. In this slide, alkyl 2,2,2 trichloroethyl carbonate formation and cleavage is given. And in another example, alkyl para-nitrophenyl carbonate formation and cleavage is given. Acetate, benzoate, and cyclic carbonates are stable to those hydrolysis conditions as cis 1,2-diol, as for example in the carbohydrates and nucleotides, and cis and trans 1,3-diols can be protected as cyclic acetals and ketals. The example for dioxo dioxolanes or dioxanes or cyclic orthoester that are cleaved by acidic hydrolysis or as cyclic ester. The example is carbonates and boronates that are cleaved by basic hydrolysis. Cyclic orthoester are more readily cleaved by acidic hydrolysis than cyclic acetals or ketals. Cyclic acetal and ketals are formed by the reaction of diol and a carbonyl compound in the presence of an acid catalyst. Dioxanes and dioxolanes are stable to alkaline condition of O-alkylation or acylation to the reduction with lithium aluminum hydride or sodium amalgam, and with an excess of benzylidene acetals either ketal to reduction by catalytic hydrogenation. Dioxane and dioxolanes are stable to some oxidizing agent such as chromic acid in pyridine and sodium hypoiodide, Pb lead acetate, uh, Ag2O silver oxide, KMNO4 basic KMNO4. These are the other example of oxidizing agent in which dioxane and dioxolanes are stable towards this kind of oxidizing agent. Benzylidene acetal react with ozone or NBS. Formation and cleavage of some important acetals and ketals are given in the next slide. First one is cyclic acetal and ketals. Here ethylidene acetal formation and cleavage is given. In this cyclic acetal and ketal, the example of isopropylidene ketals or actonides is given. The formation and cleavage of both is given. Transition to cyclic acetal and ketal, benzylidene acetal formation and cleavage example is given over here. A variety of cyclic orthoester, including orthoformate, have been developed to protect cis 1,2-diols in nucleosides. Cyclic orthoesters are more readily cleaved by acidic hydrolysis. The example here is a phosphate buffer, the pH between 4.5 to 7.5 or by 0.005 to 0.05 molar HCl, then acetonides. Two example is given here, that is methoxymethylene acetals and ethoxymethylene acetal. Dimethoxymethylene orthoester was prepared by reaction with tetramethyl orthocarbonate in presence of TSOH dioxane to protect the cis 1,2-diol system in nucleosides. It is readily cleaved by acid hydrolysis using 0.01 normal HCl to a cyclic carbonate that can then be cleaved by basic hydrolysis. Another example of cyclic carbonates is given over here. The cyclic carbonate prepared from 1,2 and 1,3-diol and phosgene or a chloroformate are stable to the acidic conditions that hydrolyze and acetonides in presence of H2SO4 and methanol at 45-degree temperature. 5 hours reaction is there. They are readily cleaved by basic hydrolysis. The formation and cleavage is given over here. Cyclic boronates have been used to a limited extent because they are hydrolyzed very readily to protect diols in carbohydrate and nucleosides. The formation and cleavage is given over here. Well, this is enough from my side. Thank you for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you very much.